Hello boys and girls, welcome to another episode of FoulkesBrau. Today we're going to continue on with first order differential equations, linear differential equations. And today we're going to look at a new technique. In the first video we looked at the separation of variables. Today we'll look at using the integrating factor. So first things first, if we look at our equation, we notice that the form is different. We've got our derivative, we've got our term, it's additive, and we have a separate term on the right hand side. So when you get it in this form, integrating factor is a good candidate. So if we really think of it, in front of the dy dx we've actually got a 1. There we've got a coefficient, a constant value, a variable, and another constant on the right hand side. So I'm not going to derive why the integrating factor works, I'm just going to show you how to do it. So the first thing we have to do is we have to find a value that we can use to get the integrating factor. And in this form it's actually very easy to see, so we write down for the instructor the thing that we're going to use for the integrating factor is this constant here in front of that variable. This is very important that you get it in this form. So we're going to tell the instructor, listen, we're going to use 2 to get our integrating factor. From there it's actually very simple. We're going to write down, in this case, rho of x is e to the integral of the value we want to use with respect to dx. That is it, that is the magic. E to the integral and whatever we chose to determine the integrating factor with. We solve this, that's going to be e to the 2x. We don't worry about the plus c just yet. From here we go back to our form that we had in the beginning and we multiply everything through with the integrating factor. So we're going to have e to the 2x dy dx plus, multiply that whole term, e to the 2x times 2y is equal to 40 e to the 2x. Let's neaten this up. E to the 2x dy dx, I'm going to bring the 2 in front, plus 2 e to the 2x times y equals 40 e to the 2x. Here's where you will do your first check to make sure that what you've used as the integrating factor is correct. If you take the derivative of the integrating factor, you must end up with this value here. Notice the derivative of 2e of e to the 2x will be 2e to the 2x. That's your first check. If you've got that spot on, you're on the right way. So now we're going to take two terms. We're going to take this term here, the e to the 2x, the integrating factor, and this second term here. And we're going to do this. We want the derivative with respect to x of the e to the 2x times y is going to be equal to 40 e to the 2x. Let's break this. D e to the 2x times y dx equals 40 e to the 2x dx. That's why we had to break that derivative. This is now simple. We take the integral on both sides. E to the 2x times y dx equals the integral 40 e to the 2x dx. That integral and that derivative are going to cancel. So on the left we're left with e to the 2x times y is, well, e to the ax, well, that's 1 over a e to the ax. So 40 over 2 is 20 e to the 2x plus c. We need to get rid of the e to the 2x because we want y on its own, so we'll divide through by e to the 2x. That means that term will cancel, that term will cancel, and we're left with that. So what we really end up with is y equals 20 plus, I'm going to bring that e up. So by the law of exponents, ce to the minus 2x. Now notice in the beginning we were given initial values. This is what we call the general solution. We actually have to find the specific solution, in other words the y of x solution. So what they're telling us here, y of 0 is 5. So we can actually fill that in. We can say 5 is 20 plus ce. Well, minus 2 times x, which is 0, is 0. E to the 0 is 1. So c is actually equal to 5 minus 20, which is equal to minus 15. We go back to our general solution and we now fill this in, and we can say y of x, in other words we're telling them now that this is the specific solution, is equal to 20 minus, well, we've got the c, let's fill it in, e to the minus 2x, and then you are done. So actually very, very simple. We want to get our derivative on its own with just the value of 1 through there. We need this additive term here, in other words the constant and the variable, and we need the constant term on its own on the right. So let's have a look at another one. So we can see it's the same sort of format. It's additive. We've got a constant with a variable, so the dy, we've got the y. Only problem is here we have an x in front, and I said to you early on, we only want the value 1 through there. So let's take this thing and divide through by x. Okay, those x's are going to cancel. So we're going to end up with the form dy dx. I'm going to write it like this and you'll see why now. 3 over x times y over 1 is equal to 30x. Remember, we've also been given initial values, so we have to find the specific solution. So we've written it like this deliberately because this is the thing that we're going to use to get the integrating factor. Notice we have a 1 here in front now, and we've got a separate term to the y. So we tell the lecturer the thing that we want to use for the integrating factor. Remember, I'm using x because we're working with x's here. If we were using t's, it would be p of t. So the thing that we want to use is 3 over x. So we tell them, right, rho of x, in other words, we're going to get the integrating factor now, is equal to e to the integral 3 over x dx. We can take the 3 out, it'll be 3 times 1 over x. The integral 1 over x is logarithm of x. So we're going to end up with e to the 3 logarithm x. Well, we can't cancel the e in the logarithm, but by the laws of logs we can bring this 3 to a power. Remember, if we have the constant in front of the log term, we can make it the power. So that is going to be e to the logarithm x cubed. The e and the logarithm will cancel, and we are left with x cubed. See, all very easy. There's nothing complex to this. You must just know your laws of logs, laws of exponents. Of course, if you can't remember them all off by hand, look in your formula and table book. You're allowed to use it. They give it to you, so use it. So we take the integrating factor and we multiply it through with this equation that we've got into this form. So I'm going to say x cubed dy dx plus, well, that's going to cancel, so that x and that x cubed will give me 3x squared y, and that should be 30 over x. Again, we're going to have a cancel and we end up with 30x squared. Okay. Take the derivative of this first term. Well, that's it there. So we know that what we used, our integrating factor, is correct. So now we take this term and the y term and we combine it and we say d dx of the x cubed times the y term is equal to 30x squared. We split the derivative so we can get a dx on both sides. We say d x cubed times y dx equals 30x squared dx. We've got to cancel that derivative, so we take the integral on both sides. That integral, that derivative cancel, and we're left with x cubed times y equals, well, 30 is going to be 30x cubed over 3, so it's going to be 10x cubed plus c. Divide through by the x cubed, y equals, that's going to cancel, so 10 plus c. You could leave it on the bottom or you can bring it to the top, it's up to you. I'm going to leave it on the bottom for now. C over x cubed. Again, this is our general solution. So if we take these values from the top, well, the 8 is, the y is going to be 8, is 10 plus c. X is 1, so 8 minus 10, c is minus 2. We go back, we tell them it's a specific solution by writing it in this form. Y of x is equal to 10, well, it's going to be minus 2 over x cubed, and you're done. Nothing really complex to this stuff. You've got to get it in the correct form. You're going to use that as your integrating factor. You tell the instructor you're using that as your integrating factor. You get the integrating factor by using e to the integral and whatever you were using to determine the integrating factor. Integrate it through and simplify. Multiply your integrating factor through by your cleaned up equation. Then split the derivative. To split the derivative so you can get the dx on both sides, you take the integral of that integral, that derivative cancel, so you basically just left with that term is equal to the integral of that side. You clean up, go back, fill in your initial values. Right, I think I've got a few more that we can do. Yep. Let's just make sure that it's in. Yes. Okay. So again, we've got a 2 here, we want 1, so let's divide through by 2. We're going to end up with dy dx, well, 2 divided by 2 is going to give me the 1. 8 divided by 2 is 4y. 48 divided by 2 is 24, e to the minus 2x. Here is the value that we need to use to get our integrating factors. So we tell the lecturer, listen, I'm going to use 4 to get my integrating factor, and rho, the integrating factor, is equal to e to the integral of whatever I chose with respect to the bottom derivative. So e to the 4x, 4dx, sorry. Well, e to the 4dx is just going to be e to the 4x, and we don't care about the c. We take our integrating factor, we multiply through by a corrected formula. So we're going to have e to the 4x dy dx plus, I'm going to bring the 4 out, 4e to the 4x times y equals 24e to the minus 2x. Take the derivative of this first term. Well, there it is there, so we know we are on the right path. Now we take these two terms and we do this. E to the 4x times y term equals 24e to the minus 2x. Split it so we can have dx on both sides. E to the 4x times y dx equals 24e to the minus 2x dx. Take the integral on both sides. That integral, that derivative cancel. So we're left with e to the 4x times y is equal to, well, the integral of this is going to be 24 over the 2. So it's going to be 12e to the minus 2x, and let's not forget the sign, plus c. Remember, we're taking the integral, so it's whatever. The a term in this case is minus 2, so 24 over the minus 2. And then plus the c. We need to get rid of the 4x if we divide through. So we're really going to end up with, that's going to be, let's just do it like this, 12e to the minus 2x over e to the 4x plus ce to the minus 2x, minus 4x. I'm just bringing it straight through. Right, so if we clean this up, that 2 is going to cancel, so we'd end up with e to the 2x. So we'd actually end up with y equals minus 12e to the minus 2x if we brought it up, plus ce to the minus 4x, and that's our general solution. If we go fill this in, 0 equals minus 12 e to the 0 plus c e to the 0, so c e to the 0 is 1, c is just equal to 12, so we can go write our specific solution. Y of x equals minus 12e to the minus 2x plus 12e to the minus 4x, and we are done. Let us take another one. This is more real world application, so I've actually drawn out the circuit here. This formula, this model describes this circuit here. We have a battery, an E value, a resistor and an inductor in series. So we know our formula for inductors is L di dt equals V. That describes the voltage across the inductor. But because we've got a resistor in series with this, we actually have L di dt. By the laws of Kirchhoff, we must account for that. So, well, voltage is resistance times current, so we've got IR equals E. That's really what is going on here. So we've got this formula given to us. They gave us some parameters, half di dt plus 10I, so you can see here I've got half a Henry L di dt plus the resistance current value 10I equals 12 volts in this case. So the battery is 12 volts. And we're given some initial values. I of the time 0 is 0. So we've got to get into the form we want. We don't want a half there, we want a 1. So multiply everything through by, in this case, 2. di dt plus 20I equals 24. It's in the form that we want. We've got a 1 there, we've got a constant, we've got a variable, and another constant. Tell the lecturer I'm going to use, so we're dealing with t, so p of t is going to be the 20 rho of t. The integrating factor is e to the integral 20 dt, which is e to the 20 t. Nothing fancy here. We take our integrating factor, multiply through by everything, e to the 20t di dt plus, I'm going to bring the 20 out, 20e to the 20t I equals 24e to the 20t. We check, take the derivative of this, e to the 20t, well, the derivative is 20e to the 20t. So we know our integrating factor is correct, and of course we've multiplied through. We need to get it so we can break this. d dt e to the 20t times, in this case, just the I term, so it's those two, is equal to 24e to the 20t. We need to break this, so we're going to say d e to the 20t times I dt is 24e to the 20t dt. Take the integral both sides. That integral, that derivative will cancel. So we are left with e to the 20t times I. If we take the integral of this, well, it's 24 over the 20, so it's 24 over 20 e to the 20t plus c. 24 over 20 will simplify to 6 over 5, so we can write this e to the 20t times I equals 6 over 5 e to the 20t plus c. We need I on its own. Divide through by the e to the 20t, so we are just left with I equals 6 over 5 plus c, will be c over e to the 20t. Bring that up by the law of exponents, so it'll be c to the minus 20t. So this is your general solution. We were given initial values, we have to go and solve them. So I at times 0 is 0, so 0 is equal to 6 over 5 plus CE, well, minus 20 times 0 is 0, so it's e to the 0. E to the 0 is 1, so C plus 6 over 5 is 1, is 0, so C is minus 6/5. We go and fill our general solution in to make it specific, so now we can say I of t is 6/5 minus 6/5 e to the minus 20t. And that is the integrating factor, gentlemen. There is really not a lot to it. You have to remember to get it in this form. Tell the instructor what you're going to use to determine the integrating factor with. Do the integrating factor, which is just e to the integral of what you chose as to use to determine the integrating factor with respect to the bottom derivative, so in this case dt. Take the Newton solution, multiply through with your integrating factor. Then we need to split this integrating factor, so we need to take the derivative of it. It's already in the derivative form because we've checked that. So if we took the derivative there, we've got this 20e to the 20t. We put it in this form, so we have dt on both sides. Well, the derivative is going to cancel, and we will just end up with the e to the 20ti. And we take the integral on the right hand side, so here we add the plus c, and then get the main variable that we're interested in on its own. Once you've got the general solution, go back, take your initial values, feed it in, and get the specific solution. I think I've got one more for us to do, which is a little bit trickier. Yes. So let's have a look at this one. So the important thing to see here is we've got 1 didt plus 2i is 16t. Be careful, you've got this variable here. If you see that, you must know you are going to try and look for substitution, or you're going to end up with a parts problem. It's in the form that we want. What are we going to use for to determine our integrating factor? Well, there it's staring right at you, the 2. So tell the instructor we are going to use, in this case, p of t is 2, rho of t is e to the integral 2 dt, which is just e to the 2t. We've got our integrating factor, not too difficult. Multiply through, so e to the 2t di dt. I'm going to bring the 2 out front. 2e to the 2t I is 16t e to the 2t. So you can already see we can't do a sub because these two t's are the same order, so that's not going to cancel. We're going to end up with a parts problem. Be careful when you're doing this, keep that term there all together so you've got it right up front to remind yourself. Okay, let's get our derivative. So we're going to say dt, the first term, our integrating factor, e to the 2t times the I term is 16t e to the 2t. Split it so we can have dt on both sides. E to the 2t times I dt is 16t e to the 2t dt. You're going to take the integral on both sides, and now might be a good time to write down your parts rule. So we're going to say, I'm going to make the u term is 16t, and the dv term is e to the 2t dt. du dt, we take the derivative, is just 16, so du is 16 dt. How do we get this? Well, now we need to break the derivative, so the only way to do that is take the integral. So v is the integral of e to the 2t dt, so v is 1/2 e to the 2t. We don't worry about the c. Again, if you're not sure how I'm doing these integrals, look in your formula table. You guys should be very comfortable with this. So what I'm going to write down now is I'm going to say that integral, that derivative can cancel. We can get rid of that in one go. So we've got e to the 2t times I equals the integral u dv which is integral is equal to u times v minus the integral v du. Again, this is in your book. I'm just doing this so that the lecturer is aware of what I'm up to. So we can go fill this stuff in again. E to the 2t times I is equal to u is 16t. V is 1/2 e to the 2t minus the integral v is 1/2 e to the 2t, and du is 16 dt. So let's neaten this up. 16 over the 16t times 1/2 is 8. So we've got e to the 2t times I equals 8t e to the 2t. 16 divided by 2 is 8. Let's bring it out. Minus the 8 e to the 2t dt. Again, now we can take the integral. E to the 2t times I is 8t e to the 2t minus 8 over 2, so it's minus 4e to the 2t plus c. We want I on its own, divide through by the e to the 2t. So I is going to be 8t e to the 2t divided by 2e to the 2t is just 8t. Minus 4e to the 2t divided by e to the 2t is just minus 4 plus c. Not too difficult. This is our general solution, so let's go fill in. I times 0 is 0, so 0, 8 times 0 is 0, minus 4 plus c. So c is going to be 4. And I forgot to put e to the minus 2t. Remember, we divided through here by e to the 2t. I forgot to actually put that e and bring it up there. I thought this was looking a bit funny, but either way, minus 2 to the 0 would be 0, so e to the 0 is 1. So our I of t is 8t minus 4 plus 4e to the minus 2t, and that is your specific solution. Not too difficult. Yep, and it is right. So the big thing, get it in the form like this, where you've got a 1 here, you've got your constant multiplied by the top derivative variable, and the right hand side will be your bottom derivative variables. In this form, that is what you're going to use to get your integrating factor. Tell your prof that that's what you're doing. To get it, you take, so in other words, the integrating factor, which is rho of t, in this case t, is e to the integral, whatever we chose to use. Solve it out, you'll end up 9 times out of 10 with e to something. Then take your integrating factor and multiply through by everything, all three your terms. Check when you've done that. Take the derivative of the integrating factor. It should end up with what is in front of your variable. If you've got that right, then you know you're on the right track. We want to take the derivative on both sides, so we can split the dt. So the derivative on the left, which we do, we split the dt, we have dt on both sides, but the integral and the derivative on the left cancel, so we just ended up with the integral on the right hand side. Because we have two parts here, we have to solve by parts, and then it's very straightforward. You get your general solution and take your initial values, feed it into the general solution, and you end up with the specific solution and you are done. Anyway, I hope that helps. Best of luck with the exams. I believe they're just around the corner. We've got 2 more lessons to do, homogeneous and non-homogeneous, and you guys should be good to go. Anyway, take care, be safe, we'll catch you soon. Cheers.